Ladies and gentlemen, thank you for being here with us today over your lunch hour to discuss climate policy. I'm Jeff Keeter. I'm the president of the George Marshall Institute, and this session is the latest in our series convened under the auspices of the Washington Roundtable on Science and Public Policy. That's an ongoing program at the Marshall Institute designed to bring together the public policy community with scientists and technologists to discuss issues ranging from environmental science, like we are today, to energy policy, to various topics in national security, missile defense, and the like. Climate change has certainly come back as a central issue on the policy agenda affecting energy, foreign policy, and tax policy. Proposals to tax carbon dioxide have been introduced in both houses of the Congress. The President spoke about it in two of his major speeches, his inaugural and his State of the Union. Secretary Kerry spoke about it. So certainly those of us in the public policy community will be considering climate issues for the foreseeable future. With the potential of billions of dollars at stake, understanding the nature of climatic interactions and the human influence on those interactions, I think, is essential for framing the policy choices and the policy actions necessary to affect those interactions. So we were fortunate today to have with us Dr. Nir Shaviv, who happened to be in the United States for other business and kindly and graciously accepted our invitation to extend his trip an extra day to come down here to speak with all of you today about his work examining the sun and its interactions with the Earth's climate. Dr. Shaviv is a professor of physics at the Hebrew University of Jerusalem. Prior to that, he was an associate professor at the Raka Institute of Physics, also at the Hebrew University. The author of any number of pieces on various aspects of astrophysics, physics in general, as well as more lay pieces on the subject of climate change and the human interactions. He holds a doctorate of science from the Israel Institute of Technology in Haifa. Dr. Shaviv, thank you for being here.
I'll begin with a succinct summary of what I want to say at the end or during this talk. First, I want to start with the problems that we have in the standard picture. And the reason is that if I come and want to present to you, say, a non-standard picture, one which does not conform to what we hear every day in the media, I have to explain why or what's the problem with the standard picture, such that when I do say whatever I will say, it won't stand in contradiction with anything that you have been hearing. So after doing that, I'll continue by saying or I'll present evidence showing you that the sun affects the climate. And then I'll discuss one mechanism to do that, which I think is the mechanism that links solar activity to climate because of a plethora of evidence. But in reality, it doesn't really matter how the sun affects the climate. The thing is that there's such a strong evidence showing you that the sun has a large quantitative effect that you have to take it into account. And the IPCC models, for example, which are considered in the IPCC report, they don't take that into account, and therefore they get distorted results because they miss a large component in the climate system. Okay, so I'll show you that the sun has a very large effect, something of order 1 watt per square meter, which is comparable to the anthropogenic effect. And it means that some of the warming over the 20th century is human and some is solar. But the big difference between with the conclusions that I reach and say the standard IPCC conclusions is that the climate sensitivity is on the low side. Namely that if we, for example, double the amount of CO2, we will increase the temperature by something of order 1 degree, and not say 1.5 to 4.5 degrees, which is the canonical range of the IPCC. Okay, so let me start with the common view and what the problems in it are. The view expressed by the IPCC, for example, is the following. We know that the energy budget over the 20th century has changed, primarily because of anthropogenic forcings. That's expressed in the graph on the left. You see different changes in radiative forcings, and the largest contribution is that of the green one, which is the greenhouse gases. If you then take these radiative forcings and you plug them into global circulation models and you start cranking them, what you'll find is that there's a temperature increase, and you can in principle explain the temperature increase that we have seen over the 20th century with these radiative forcings, which means that these are radiative forcings, and the models are correct because they can give us predictions which are consistent with observations. Case closed. We humans are responsible for the temperature increase, and that's that. Well, not so simple. There are quite a few problems. For example, the range of predictions, or say the range of sensitivity, is something like 1.5 to 4.5 degrees, and it has been since the first IPCC report. Actually, in the last report, in the fourth assessment report, they changed it to 2 to 4.5. This means that the change in temperature over the time span since the first assessment report should be within the range of predictions, because the range of predictions didn't change. Again, the first assessment report said that the sensitivity is 1.5 to 4.5 degrees. Okay? 20 years later, the claimed sensitivity is virtually the same. This means that the global temperatures should have been within the range of predictions made by the first IPCC report. But they're not. If you look at what has happened, you see that the global temperatures are roughly at the lower range of the estimated, they're roughly at the lower range of the temperature increase. So in any reasonable theory, or any reasonable discipline, what people would do, they say, okay, we have predictions, we have observations, the observations don't fit the predictions, or at least they fit just the lower edge of it. This means that something was wrong with our predictions and we should go and update them. But what the IPCC does instead is every 6 years they reset their prediction clock. They make predictions again every 6 years. So by definition, we're always within the range of predictions. So they cannot be wrong this way. Okay, another problem is that the location of the warming is not where it has been predicted. Yeah, if we look at this graph, which is by Douglas et al., we see that the models give you that the warming should have been larger, higher up in the atmosphere, and this has to do with the way that CO2 heats, and that's by making the whole atmosphere transparent. Whereas if you look at radiosonde data, you see that the warming at the surface was larger than the warming at other altitudes. So if you think that that CO2 warming should have had some fingerprints with which you can prove that it's CO2, you don't. You see that the fingerprint doesn't match. Another problem is that the climate models are too sensitive. If you look at this graph from the third assessment reports of the IPCC, you see that there's a general agreement between the models in gray and the observations in red. But if you look more carefully, you see that every time there was a very large volcanic eruptions like Krakatau or Pinatubo or other stratospheric piercing volcanoes, the models give you that the temperature should have decreased by quite a lot. Why is that? The volcanoes put a lot of aerosols or dust in the stratosphere. That dust blocks some of the sunlight and Earth should cool. But because the models are oversensitive, you actually see that the reduction in the temperature by the models, you see here that during Krakatau the temperature decreased, the temperature didn't decrease at all, whereas the models gave you that the temperature should have decreased by quite a lot. In fact, you can average over the the temperature reduction following the 6th strongest volcanic eruption since Krakatau, and you see that the average reduction is only about 0.1 degree. For comparison, the climate models that give you, or that explain the 20th century, give you that the temperature reduction should have been somewhere between 0.3 and 0.5 degrees. So obviously the models are too sensitive. Another problem is that the models can give you, in fact, any sensitivity that you want. The reason is that if we put in more CO2 in the atmosphere, the canonical number is that we change the radiative budget by 3.8 watts per square meter. This should hit the surface, but in reality, this is not the only thing that happens, because if you hit the surface, if you hit the oceans, you evaporate more water. If you have more water vapor in the atmosphere, you have more greenhouse gas, so the temperature should increase by more. But if you have more water vapor in the atmosphere, you also have more cloud cover. And if you have more cloud cover, you will decrease the temperature. So in fact, it turns out that the single largest unknown in global circulation models, which governs the value of the sensitivity, is the recipe with which cloud cover is described in the models. The thing is that we cannot predict ab initio how the cloud cover will change. We don't know if we change the temperature by so and so or the humidity by such and such, we do not know how to calculate how much the cloud cover will change. So this change in cloud cover is put in by hand as a recipe in the climate models. And you can see by this graph, which was published already in 1989, the situation didn't change over 20 years. You see that on the x-axis, we have the intrinsic feedback that the models have to a change in the cloud cover, namely by how much the energy budget changes due to changes in the cloud cover if you change the temperature by a given amount. And here on the y-axis, you have the climate sensitivity, by how much the temperature will increase if we double the amount of CO2. And you see that the single largest, or you see that if you change the cloud cover feedback, you basically govern or determine what the climate sensitivity is going to be. So this is the single most unknown in global circulation models. All the rest is secondary to that of clouds. Okay, another problem is that there's no fingerprint that tells you that CO2 has a large effect on climate. You might say, just a second, we've seen Al Gore's movie, and in the movie we have seen this graph where he has shown us that there's a correlation between changes in the temperature, which you have in red, that's the temperature, and in cyan you see the changes in CO2. This is derived from ice cores, in this case in Antarctica. And it tells us that, you see that there's a large correlation between CO2 and the temperature, and that tells us that, he tells us that when there is more CO2, the temperature is higher, because he wants to make us think that CO2 has a large effect on the temperature. What he doesn't tell us is that in all cases where you have a high resolution in the ice cores, you see that the CO2 follows the temperature. There's a lag between the temperature and the CO2 such that obviously changes in the temperature change the amount of CO2. We expect the CO2 to have some effect on the temperature as well, but we cannot derive it from this correlation. Now, why does the CO2 change when you change the temperature? It's very simple. Most of the CO2 in the atmosphere ocean system is CO2 which is dissolved or in the oceans, or it's actually more complicated than the simple dissolution because of chemical reactions. But most of the CO2 is in the oceans, and there's a chemical equilibrium between the CO2 which is in the atmosphere and the CO2 which is in the oceans. And this equilibrium depends on the temperature. So if you heat the oceans, you release the CO2 on a time scale of several hundred years from the oceans to the atmosphere. Okay? The same thing happens if you take this can of Coke and you leave it in your car in summer. If you open it, you'll have some mess, and the reason is that you can dissolve less CO2 in the Coke when it's hot. Okay, on long time scales, there were large variations in the CO2 which didn't correlate with any temperature variations. On small timescales of tens of thousands of years, we know that there's this equilibrium, but on long timescales, the amount of CO2 in the system changed by quite a lot, and that's because of geological activity. You have volcanoes emitting CO2, and you have CO2 which settles as limestone and is recycled back in Earth. So you see that there were large variations in the CO2 over the past 500 million years. Okay, you see here large variations. This is a logarithmic scale, so it's a factor of 10. And on the other hand, you see that the temperature on Earth over this time scale didn't correlate whatsoever with the CO2. So you can use this to place an upper limit on the effects of CO2. And when I did it together with my geological colleague, we immediately became persona non grata, because how dare we say that CO2 doesn't have a large effect on climate? It doesn't, because you don't see that there's a large effect. Another problem is that, one argument that global warming over the 20th century is unique, because of humans, is because it is unique. We all know about the hockey stick, which we know is the hockey stitch, because they stitched the thermometer data beyond 1960. But this argument was that the warming is unique, and therefore it must be human. But we know that it's not unique, and the hockey stick is, rubbish. Another problem with the standard model is that we're told that the models can fit the 20th century, and therefore they're valid. But because the climate sensitivity is not known in the models very well, and because of the forcing is not known very well, because there's the large indirect aerosol effect, in fact, the models could have explained anything. If you look at the draft report of the fourth assessment report, you see here the probability distribution function that we may have caused a positive effect on the energy budget, or maybe we have caused a negative effect on the energy budget. If there was global cooling over the 20th century, the same scientists would have been able to explain the cooling with the same theory, the same models, and the same uncertainties. Okay, another argument that the 20th century is human is because we have nothing else to explain the warming with. But there is, and that's the sun, and this is the rest of what I'm going to talk about. It turns out that the sun changes its activity. On the bottom right, we see the sun in UV at different times over the solar cycle. And we see that the sun changes its activity, and this activity manifests itself as changes in the amount of UV, in the strength of the magnetic field, in the number of sunspots, in the strength of the solar wind, and other things. And the solar variations, you can separate the solar variations to different time scales. The main variation is that of an 11-year or almost an 11-year, roughly an 11-year cycle over which the magnetic field flips polarity. Every 11 years, the north and the south magnetic poles of the sun switch polarity. On longer timescales, you have secular variations which modulate this 11-year solar cycle, whereas on short timescales, you have things like coronal mass ejections and things like that, which we know because those things disrupt radio communication on Earth, for example. Okay, so those variations in solar activity manifest themselves as changes in the climate on all the different timescales. Here you see one of the nicest correlation whatsoever, which I think exists. At the top you see a reconstruction of solar activity based on carbon-14 from tree rings all over the globe. Carbon-14 is formed by spallation of high energy particles reaching Earth from outside the solar system, particles which are called cosmic rays. They hit the atmosphere, and they can break nitrogen and oxygen atoms into, or nuclei into smaller pieces, including carbon-14. But this flux of cosmic rays is modulated by the solar activity. And the reason is that the sun has a solar wind, When the wind is stronger, we get less of this cosmic ray, so we get less of the carbon-14. So this thing at the top is a proxy of solar activity. At the bottom, we have oxygen 18 to oxygen 16 isotope ratios in stalactites in a cave in Oman. And the isotopic ratio of the oxygen 18 is a proxy of temperature, in this case a proxy of the temperature of the Indian Ocean, because water with oxygen 18 is heavier than water with oxygen 16, which is the common isotope. So the evaporation rate is different, but this ratio depends on temperature, such that if you have an ocean with a different temperature, you'll get a different systematic ratio of or changes in the isotopic composition. So basically, you see changes in solar activity at the top and climate, the temperature of the Indian Ocean at the bottom. Okay, you see a very nice correlation, right? So it tells us that the sun is affecting the climate, unless we believe that the climate is affecting the sun. I don't think so. Not just yet. Okay, this is another example. In blue, we see again the carbon-14 from tree rings, and in black, we see a record, or a marine record, for the climate in the northern Atlantic. Basically, what happens is that when you have colder winters, you have icebergs drift further south, and when they melt, they deposit the ice-rafted debris further south, that if we take an ocean bed core, like you see at the bottom right, we can detect whether it was a colder winter or a warmer winter. So you see here the correlation between the solar activity and the climate in the northern Atlantic. Okay, so there is a very large link and between solar activity and climate. And I'll tell you now what I think the link is and what the evidence for it is, and then I'll show you that you can actually measure how large the solar climate effect is and why it necessarily has a large effect on climate. Okay, so the way that the sun affects the climate is the following. We know that the sun changes its activity over the 11-year solar cycle. This manifests itself in a change in the solar wind. The solar wind modulates the flux of these high energy particles which are coming from outside the solar system. And in fact, the interesting thing is that those particles are the dominant source of ionization in the atmosphere. I mean, here in the room, we might have radon from the concrete, which governs the ionization, but if you go out to the atmosphere, it's primarily cosmic rays. So it means that if we have a more active sun, we have a stronger wind, we have less cosmic rays, and therefore less atmospheric ionization. And today we know that this ionization plays a role in the formation of cloud condensation nuclei, such that if we have less ionization, we form less cloud condensation nuclei, and we get clouds which are less white. They reflect less of the sunlight, and the temperature is higher. Today we know that every one of those links that I mentioned is operating. There's evidence for each one. First, we see that the cloud cover varies together with the solar activity. You see the 11-year solar cycle in cosmic rays in red, and we see the low altitude cloud cover in blue, and we have here 20 years, which is like 2 solar cycles worth of data. Another way that you can see that the cosmic rays are affecting the climate is on a long geological timescale. As we roam the galaxy, we change, or the galactic environment around us changes, and the astronomical data tells us that we should pass the spiral arm of the galaxy every about 145 million years. And you can reconstruct this cosmic ray flux using iron meteorites, and when you do that, you see this 145 million year periodicity, which lo and behold synchronizes with temperature variations over the same time scale. These temperature variations were derived with looking at oxygen 18 to oxygen 16 isotopes in in fossils, in this case marine animals living in tropical oceans. Okay, so there's a correlation between cosmic ray flux and climate. On very short time scales, you can have events which are called Ford-Bush decreases, which are caused by gusts in the solar wind. You have a gust in the solar wind, so several days later we get a reduction in the cosmic ray flux reaching the Earth. You see that in red. And this reduction in the cosmic ray flux then manifests itself as reduction in the number of aerosols that you see over the oceans, and reductions in different cloud properties as derived by different satellite data. So you see that also on short time scales, if you play with the cosmic ray flux, you play with the cloud cover. Okay, there's also experimental evidence. This experiment was carried out in Copenhagen. They took a chamber which mimics conditions you find over the oceans, and then started changing the rate of ionization that you have in those chambers. And what you see here in this graph is that when you change the ionization rate, in this case, the number density of ions that you have in the chamber, you change the nucleation rate of small condensation nuclei, which later have to grow and become large cloud condensation nuclei. This experiment was repeated in CERN, and they published the results a year and a half ago. You again see that if you increase the the ionization rate in the chamber, you increase the formation rate of condensation nuclei. Okay, so you can also go to the lab and see that the effect is taking place. Now, what you see here is something else. This is pollution that you get from ships. Ships traveling in international waters burn dirty fuel because there are no laws forcing them to burn clean fuel. And these exhaust particles then serve as cloud condensation nuclei. So here, this is the marine layer of clouds opposite the shores of California and Oregon. And every time a ship passes by, it leaves a trail of exhaust particles. And these exhaust particles, in that area, you have many more cloud condensation nuclei, such that when you do form the clouds, you get many more droplets. So they have a much larger surface to volume ratio, which means that they are whiter, they reflect more sunlight, and we can clearly see them in the satellite data. Okay, so this shows us that if we play with the density of cloud condensation nuclei, we play with the characteristics of the clouds. Okay, so how large is this link? Well, the first thing you can do, you can look at the change in the cloud cover, and then use some satellite data. In this case, it's the Earth Radiation Budget Experiment, to translate this change in cloud cover into a change in the energy budget. And you find that the peak-to-peak variations over the solar cycle are about 1 watt per square meter, which is comparable to the change in the energy budget associated with the anthropogenic gases over the 20th century. For comparison, here at the bottom you see the change in the solar constant. There are satellites which continuously monitor the output from the sun, and the sun is not constant. It changes its irradiance by just a little bit. This little bit that corresponds to a change of about 0.17 watt per square meter, or the peak-to-peak variations over the solar cycle. So you see that the change in the energy budget associated with the cloud cover, because of the cosmic rays, is about 6 to 7 times larger than the changes in the irradiance. Now, when you find in the IPCC, when it says in the IPCC that we did consider solar effects, what they mean is that they took this small effect into account, but they totally disregarded the large effect that takes place because of the amplified effects. There's another way you can measure the energy budget change associated with the solar cycle. Here you see over the past 80 years, you see a reconstruction of the solar flux in red, so you can clearly see the solar cycle. And overlaid on it in black, you see the rate of change of the sea level. Okay? Now, on short timescales, most of the change in the sea level is because of thermal expansion. So when we are at a solar maximum, Earth gets more radiation in because of the change, because of a lower cloud cover. So the oceans heat, and as they heat, they expand. And you can see these cyclic variations in the sea level in sync with the solar cycle. You can then take this thermal expansion and calculate by how much, or what is the change in the energy budget. In a sense, you're using the oceans as a very large calorimeter. And the number that you get is that the peak-to-peak variations in the radiative forcing is, lo and behold, about 1 watt per square meter. So everything is consistent. Okay, so you can estimate this 1 watt based on cloud cover or sea level change rate, or you can use buoy data measuring the ocean heat content, or you can use the sea surface temperature change. And in all cases, you get variations synchronized with the 11-year solar cycle, and they're about 1 watt per square meter. And again, for comparison, the changes in the solar irradiance are roughly 6 or 7 times smaller. Okay, so what does that mean if you want to understand the 20th century? Over the 20th century, the solar activity has changed. It has increased. Okay, it increased dramatically between 1900 and the middle of the 20th century, and then there were like small variations. There was some decrease and some increase. If the sun has a large effect on climate, it means that this increase in solar activity should translate to some warming of the climate. So what we did, the student and I, is try to construct a model which will take that into account. Basically, we built a climate model which includes different components. It could be the land, the oceans, the diffusion of heat into the ocean, which is very important because that's where all the heat in the climate system is stored. And we left everything as a free parameter. We said, we don't know what the climate sensitivity is. We don't know what the real effect that the sun has on climate is. We don't know what the coupling between the land and ocean or the diffusion. We left everything as a free parameter, and we asked, for what range of parameters can you explain the 20th century? So when we did that, we found that we can explain the 20th century very well. And what do I mean by very well? I mean that the difference between the reconstructed temperature and the real temperature is about 0.1 degrees Celsius. For comparison, global circulation models at best give you typical discrepancies of about 0.2 degrees. So with all their large simulations, they do twice worse than what we do with our relatively simple model. Now, the reason is that they don't include the solar forcing. If they would have included the solar forcing, they could have explained the 20th century with a much lower climate sensitivity, and then they would have found that there are less discrepancies, for example, when we had large volcanic eruptions. Okay, so what does it imply? How do we understand the 20th century with this? The standard picture, or the one that we hear time and again, is the following. We have some changes in the radiative forcing associated primarily with humans. And we have some observed temperature change over the 20th century, which we want to explain. For the given change in radiative forcing which are primarily anthropogenic, we now need a relatively large climate sensitivity in order to explain the given temperature, the observed temperature increase. If you now have a large climate sensitivity and try to integrate it forward in time for given emission scenarios, you will then get large temperature increases over the 21st century. But if you have additional positive forcing, in this case the sun, which is comparable to that of the anthropogenic forcing, in order to explain the same temperature increase over the 20th century, you now need a low climate sensitivity. And this low climate sensitivity, if you now integrate it forward in time, will give you a smaller temperature increase over the 21st century. Okay? How small? Well, what we can do is we can take the range of model parameters that explain the 20th century. I mean, there's a wide range of parameters. Some of the parameters we cannot constrain, for example. And integrate over the 20th century. We fit the 20th century, and then integrate with those parameters forward in time and ask the question for a given emission scenario, by how much will the temperature increase? And this is what we get, and for comparison, these are the IPCC scenarios. Okay, again, the reason is that if you include the sun, and we know that the sun has a large effect because we see it in the clouds and we see it in the oceans. We know that it's there. If you include the sun, it means that there's an additional radiative forcing over the 20th century, and it means that you need a lower climate sensitivity to explain everything. This lower climate sensitivity then manifests itself as a lower temperature increase over the 21st century. Okay, so I'll summarize. The problems with the standard picture. Everything I said here is not inconsistent with the data that is used or you find in the IPCC reports. Okay? The main difference is that in the standard picture, the sun is not taken into account, but the sun does have a large effect on climate. We see all the evidence and we can quantify this effect. It's large, and when you take it into account, you find that some of the warming over the 20th century is not human, it's solar. But the really important number, I mean, it doesn't really matter if a third of the warming is anthropogenic or 2/3 is anthropogenic. The really important number is what is the climate sensitivity, by how much will the temperature increase if we say double the amount of CO2. And this value is something of order 1 degree for a, say, standard CO2 doubling scenario. And with this, I'll end. I'll quote Al Gore quoting Samuel Clemens, who said, "What gets us into trouble is not what we don't know, it's what we know for sure that just ain't so." That's it.
Well, before I open it to the floor for questions, I'm going to use my chair's prerogative and ask you the first one, which is, in your view, what's the rationale that's offered by the IPCC or others for dismissing the sun or not taking it into as large account as you'd suggest that they should?
It's inconvenient to, I mean, for them it's inconvenient to take it into account. So any slight debate or uncertainty that there is immediately amplified. For example, we're not sure what all the microphysical effects which are responsible for growing the clusters of, growing the condensation nuclei and letting them grow all the way up to cloud condensation nuclei. We are not sure we know all the microphysics. So immediately they'll say, okay, we don't know what the mechanism is, so it's not there. But the evidence is there. We see that the evidence is there. And it doesn't matter what the actual solar climate link is, we see that it operates and we should take it into account. It's then a very interesting academic question of knowing the exact details of this mechanism. Okay?
Randy, we'll work our way to the back. Go ahead.
One of the issues that we have is we have had 4 reports and now we're on the way to the 5th IPCC report. The question is, are there any papers out there that they should have paid attention to that may have shown up in the AR5 that they discarded? We got to find some way to say, look, if you left these papers out, you can't ever get the right answer.
This was published in 2008. It proves that the sun has a large effect on climate. Nobody has discredited it. Nobody found a way out to explain it some other way. It proves that the sun is important. If it's not in the 5th assessment report, it just means that they're trying their best to ignore the data. the evidence.
Who are the authors?
I am.
You are.
All right. Questions? Ken?
Ken Hopoulos. Your Oman cave study, has that been replicated many times in other locations?
It's not mine. It's by a group in Heidelberg headed by Professor Mangini. So he's German, even though the name doesn't suggest. There wasn't a group that redid the analysis in the cave in Oman, but there were other similar analyses looking at, say, caves in China or the seabeds in Northern Atlantic or other places on Earth, and you see similar correlations. So the answer is not exactly the same thing, but similar things other places on Earth.
Marlo?
Dr. Shabib, the increase in solar activity in the 20th century, in your view, is that a century, part of a century-long cycle, or is it an even longer cycle? And what should we expect for the 21st century? Do you think the sun is becoming quieter or less active, or could we get a repeat of the same, where we have both the increase in solar activity and the increase in greenhouse gas emission levels combining to give us a larger warming than the actual climate sensitivity from CO2 doubling alone would give us?
Okay, the variations we see over the 20th century in solar activity are part of long-term variations that the sun has on a range of timescales from several decades to centuries and maybe even longer. The problem is that we cannot really predict exactly what the sun is going to do, and the reason is that it originates from the fact that the top 40% of the sun are convective. It's like you're boiling a soup on a stove, and you see that at some point everything is moving like that. The top 40% of the sun are exactly the same. And just as much as we cannot explain when we'll have a big blob of soup rising in the middle, we cannot explain when the sun will be more active, because it's a chaotic process. There is some spectral structure on different timescales, but not much more than that. What we can do is look at what the sun has been doing historically and see that it ranges in activity between a range of states. It virtually doesn't go less active than what it was in the Little Ice Age, 200 and more years ago. No, 300 years ago. And it doesn't go, it doesn't become more active than what it was in the past 50 years. Okay, so this is the range of activities that we see that the sun has. This means that we don't know what the sun is going to do on the 21st century, but we can expect it not to become more active than what it has been. So it's not going to contribute some warming. In the range of reconstructions that we have made here, we actually try to take the sun into account by taking the same spectral structure of historic solar activity, randomizing the phases and saying, okay, this is now what the sun is going to do in the future. And then you have many realizations. So these predictions actually consider that you get a little bit of cooling, or you can get some cooling because of solar activity decrease.
Why don't you explain this chart again, just so we make sure that folks
Okay,
understand what you're telling
this
them.
part of the chart is based on allowing the model parameters to vary whichever they like, such that the predicted temperature fits the observed temperature. Okay, we don't know anything about the climate. We allow all the climate parameters to vary. And so then we have a set of model parameters that fit the data. We actually degrade the data so that we'll get a larger range of parameters so that we can estimate what the probability distribution function is for the different parameters. Some of the parameters are better fit, and some others are better constrained, and some others are less constrained. And then you have this range of parameters, and for each one, for each model, you can integrate forward in time for a given emission scenario. Suppose you're going to have a given amount of CO2 in the atmosphere over the next 100 years. By how much will that change radiative forcing? You plug that into the model with one realization of the model parameters, and then you get one spaghetti here.
Okay. In the background?
Hi, my name is Dave Christie, and I have just one quick comment on what I see as what's going on here in terms of why they're not taking into account solar activity. In 2009, when the Copenhagen Summit occurred and China and India said we're not going to shut down our industrial advancement just for a supposed global warming problem, which was not scientifically verified, and as your data does show indeed that solar processes play a large role. And soon thereafter, Sir David Attenborough, who is one of the main spokesmen for an agenda which, as he said, we needed to reduce world population from 7 billion down to 1 billion. Some people say even less than that. I'll just make a comment and then I have a quick question, which is I think this is a political agenda. It is to prevent industrial development as part of the depopulation agenda. And you can comment on that if you will, but there is a faction that has pushed this for, frankly, decades and have used scientific hoaxes to pursue that political agenda. Now my question is, the Russians have proposed what's called the IGMAS, the International Global Monitoring Aerospace System, and deals with the very issues of space weather, that not just solar activity, but there is potentially even galactic activity. Some hypothesize that features of the Crab Nebula may play a role in even weather here on Earth. I'm not saying it does or doesn't.
No, it
but
won't.
that's, part of what the IGMAS is looking at, and it's actually under the umbrella of what they have called the Strategic Defense of the Earth, which is a revival of the old SDI concept of Reagan, and actually coincidentally my associate Lyndon LaRouche, but
Okay.
upgrades also the...
So the question's about the IGMAS.
And the SDE,
Okay.
which is Strategic Defense of
Got
the
it.
Earth.
But I didn't understand what the question is.
Should we be doing this satellite program with the Russians? And I think.
I
the
don't have,
extension-
okay, so
extension would be
the answer in short is that I don't have any political views. I mean, I do have, but they're totally irrelevant. I'm a scientist, this is the scientific data, and it's up to the politicians to, to look at what the data is and decide what's best.
No, you had a very interesting, there is one thing I want to pull out of that. You had a very interesting chart where you showed that, I think it was the sun moving through the galaxy.
Yeah, it's a little bit inaccurate. It was taken out of a film, but
Sure.
It's inaccurate because in reality the spiral arms themselves, the spiral arms are waves which are moving at one velocity, and we are moving at another velocity relative to the spiral arms.
Well, why don't you clarify for us when we make this journey, when the sun and we going along with it makes this journey through the galaxy, you talked about different ratios here on Earth that allow you to measure what the effects of going through different points are. Reiterate that for us, if you would.
Okay, over the past billion years, Earth has had 7 ice age epochs. Every 145 million years on average, it was cold on Earth such that we had ice caps. 100 million years ago, for example, we didn't have any ice caps on Earth, and alligators sunbathed in Alaska. Well, there was no Alaska, but where Alaska is, sunbathed and lived happy. So there is this large, there are these large variations in the climate over this time scale of a billion years. That's on one hand. On the other hand, you can reconstruct the cosmic ray flux using iron meteorites, and when you do that, you find that Basically, okay, just before that, the reason you can reconstruct the cosmic ray flux with iron meteorites is because meteorites roam, or when they break off their parent body, they roam the solar system, and their surface is exposed to cosmic rays. So you can then look at the products of this interaction between the cosmic rays hitting the meteorite, and if you look at those products, you can calculate how long or not exactly how long, what was the total flux of cosmic rays that this meteorite was exposed to. And then if you have a bunch or a cluster of or many meteorites, you can use this data to go back and reconstruct what the cosmic ray flux was. And when you do that, you see that you see 7 oscillations in the cosmic ray flux, which just synchronize with the appearance of ice age epochs on Earth. And the reason is that those changes in the cosmic ray flux are very large, they're like a factor of a few, as compared to, say, the 10% effects that you have because of solar modulation. So it translates into a 5 or 10 degree change in the climate, which is huge, and which is why we can see it. So
I think there was a question in the middle.
My first 2 questions were articulated better than I could about the IPCC and the long-term future. So thank you for asking them. I suspect, I mean, this is just a guess because the fifth assessment report's still in process, but I think the people that do these things work very hard to take account of the literature. And so my suspicion is that they will revisit the solar variability component of the radiant forcing, and we will see some of this work reflected in the IPCC. So I'm confident that when it finally comes out, is that some of this stuff will be reflected. I am kind of thinking about the long-term future of the Earth, and whether it's the sun variability or the greenhouse gases or the molecular cycles or the galactic cycles. It's the first time I actually seen a plot of 145 million year circle around the center of the galaxy. But it does seem to me that the future is not good. Whether we have warming from the sun or whether we have warming from these other causes, it looks like we're heading to warming, and so I think this has implications for adaptation, regardless of the cause. And when you refer to the ice ages, is that there was a science article in October of last fall. It was researched by Chinese, where they did look at the Triassic, where we had a lot of the volcanic activity and Siberian traps and huge oxidation of coal and fossil resources at the time, where CO2 elevations went very high, and there was no life in the sea at that time, and there was no higher forms at least, and the mid-latitude zones were baked, and most life on Earth did migrate to the poles at that point. So that was, I think, about somewhere between 2,000 and 3,000 parts per million. We're at 400 and probably heading for 1,200 without any check. And so I'm wondering if you can integrate this into a bigger picture of where we're headed as a race, over the next century or so. And it does seem to me that we should worry about some of those things.
First, for your comments, I hope that the IPCC will take a broader look at the literature and incorporate what we know about solar effects on climate. Whether they'll do it or not, I don't know. I'm not a prophet, even though I come from Israel. As to your second question/comment, the conditions on Earth have always changed, and they have always changed for a variety of reasons, whether it's changed the amount of greenhouse gases or changed the amount of other conditions. 450 million years ago, we had more extensive ice caps than we have today, and the CO2 was around 3,000 parts per million, so like 10 times as much as we have today. So there are other things other than CO2 which are affecting the climate. Some of the things we can maybe try to think that we can control, and some of the things we definitely cannot control, which means that the best policy is to be able to adapt. I mean, being able to adapt to different changes is probably the best thing. But that's in the long run, because I don't think that the conditions over the coming century are going to be significantly different, that in fact we'll have to do any adaptation whatsoever. I'm also doubtful that we are going to double the amount of CO2 over the 21st century for other reasons, because I don't think we are going to be burning fossil fuels in, say, 50 years, because we'll have other things, because I'm optimistic that I know the price of photovoltaic cells will decrease significantly like it has been, but now it isn't. I mean, now it's not worthwhile subsidizing inefficient technology. Just invest in developing the better alternatives. But over the coming century, I don't think we're going to have any problems. I'm not worried that my children or my grandchildren, which I don't have yet, are going to have any problems whatsoever.
Well, if I recorded it right, I think one of your last slides you said the takeaway was that you saw a 21st century temperature change of roughly 1 degree
Yeah.
Celsius. And it's this chart that validates
Yes,
that?
yeah.
Okay.
Ask yourself, if you would have been asked in the year 1900 whether you should worry about a 1 degree temperature increase, because that's what the temperature is going to increase over the 20th century, should that have been a source of concern in the year 1900? I think in the year 1900 we had a lot of other things to be concerned about.
Sure. And so the increase, let's just clarify that, because if we're talking about a 1 degree change over the next 100 years, you're saying we had a 1 degree change over the prior 100
Well,
years?
0.7, 0.8, something like
Okay.
that.
Sir?
Hi, my name is Michael Kirsch. I just wanted to thank you so much for your work. I saw the Cloud Mystery with you and Svensmark, and it was so good I watched it a second time, and it just became so clear the relation of the magnetic flux of the sun bringing in the cosmic rays, and then the additional with the spiral arm galaxies. What I'm wondering is, because it is so, the view takes into the context in which the Earth is, and it's so rigorous, the matchup of the cycles and all the work you've done. What would you have Congress, and if you don't want to pose it like that, you don't have to, but what can Congress do here? What could be done to bring this knowledge? Because almost everybody in Congress thinks that it's just CO2, that's all you have to think about. And so if there could be a hearing, or what could be done here in Congress, and what would the panel look like? Who would be on the panel in a full congressional hearing on this subject to educate people on this and get this circulated through as rapidly as possible, so that the view is not limited to this Thomas Mann hockey stick thing.
I think Congress can do things on two levels. On one level, there is the part of education, like you can get a better exposure. On the other part is the question of funding. The thing is that I'm always being told, oh, your point of view is well funded or whatever. That's rubbish, because if you look at just the scientific, the money that goes into scientific research, the amount of money that goes into, say, the standard picture that we see every day of climate research in that direction is orders of magnitude larger than the alternative views, which are very important if you want to keep the scientific debates alive. So I don't know how much Congress can actually help, funnel money into, a broader range of disciplines, or not disciplines, but views. But yeah, okay. So I don't know what to say more on that aspect because I'm a layman in politics.
But who else should we be, I think the other interesting part of his question is, who else should we be bringing here to talk to the general community about about some of the topics that you've raised or other aspects of climate science that you may have observed that may challenge the traditional view or have interesting observations that are underappreciated, let's say, in the traditional view?
I mean, I have colleagues who are all. I have several colleagues that think similar things. The interesting thing is that each one came to this picture from a different point of view whatsoever. I have a Canadian colleague, Jan Weiser, who got into this field from the realm of geology. And there's Henrik Svensmark in Denmark who started his career in meteorology department, and at some point when he suggested that the sun has a large effect on climate, people didn't greet him good morning in the corridor. It's like strange. So there are a lot of other people, and people who are good scientists who can expose their point of view coming from different directions, and then you can see that it adds up to a consistent picture.
Sure. I think that's important to have a diverse set of perspectives. I think you had a question, didn't you, sir?
Yes. Dr. Svensmark said that he thought that the high energy cosmic rays had more of an impact on clouds than the lower energy cosmic rays. Do they leave a separate track in the geological record that you can track back and look at? Because I've never seen that kind of a thing directly.
Okay, cosmic rays come at different energies, from a GeV, which is 10 to the 9 electron volts, to 10 to the 20 or more electron volts, which is one subatomic particle coming with the energy of a bullet. So there's a very wide range, but what's important for climate is actually the bulk of cosmic rays which can penetrate the atmosphere. Now, most of the energy in cosmic rays is at the lower end, at 1 GeV, but those particles are not energetic enough to penetrate the atmosphere. The particles that can penetrate the atmosphere are at an energy of about 10 GeV or more. So any record which is left on Earth is a record of those particles, which are also responsible for changes in the ionization and the cloud cover. It's only records which come from outer space, like meteorites, which can be sensitive to lower energies as well.
In the back.
Thank you. I'm Jane Leggett from the Congressional Research Service. I have a couple quick questions and then a slightly longer one. First, do you have a journal citation for the modeling work that you put up there?
Yes, I have. I can, if you email me, I can give you my business card, and then you can email me, and I'll email you back the.
Second is, if I'm understanding, you're saying that the bulk of the solar contribution is coming from the high energy cosmic rays. And can you tell us, maybe I missed it, what the change has been over the period from the 1970s to the present, over that period on average, or?
Okay, so the change in the atmospheric ionization, which is governed by 10 GeV particles or more coming from outside the solar system, is about 10% over the solar cycle. And the long-term secular variations are comparable to that. So this is of order the effect that we have seen over the 20th century. Now, the solar activity peaked in the 1990s, which means that the solar contribution is now diminishing. But because the system has a large heat capacity, it takes time. Even if we start decreasing the forcing, it takes time for us to see this manifested. It's for the same reason it's warmest at say 2 o'clock in the afternoon, or the warmest month is in August, not in June, and that's because of the heat capacity in the system.
So what's that lag time, when would you expect to see?
Well, the lag time is comparable. It's shorter, but comparable, of the same order as the time scale of the change forcing. I mean, if I heat the oceans for 50 years, it will take me several decades to get rid of this energy. If I heat the oceans for 1 year, it will take me several months to get rid of this energy, because the heat penetrates further inside the oceans. So if I heat Earth over several decades, because I had a large solar forcing, it will take me a few decades to get rid of this excess heat.
Dr. Singer?
I've looked at the forthcoming fifth assessment report of the IPCC. Their chapter 10 deals with attribution, where they try to back up their conclusion about anthropogenic global warming. The only evidence they cite is a discrepancy, a claim discrepancy between observations of surface temperature and the unforced climate models. There's a discrepancy. They say the difference must be due to greenhouse gases. My question is, could you comment on this, and could you also comment on whether the IPCC is gradually adopting any of the evidence that you've presented about solar activity and cosmic rays? Are they at least quoting the work that you cited here today?
The answer to your first question is, okay, so let me repeat it in a little bit different words. What they do in the IPCC, they quote results of simulations of models which don't include the anthropogenic effect and models which include the anthropogenic effects. And they say without the anthropogenic effects, we cannot explain the 20th century warming. We get a large discrepancy. The reason they get that is because the models that don't include the anthropogenic effects don't include the real effect of the sun. They include only changes in the solar irradiance, which are about 6 or 7 times smaller. So they don't, their models that don't include the anthropogenic effects are simply wrong. Then comes the question whether the IPCC, or which references are they going to include in the fifth assessment report. The answer is that I'm not on the panel, so I don't know. I just saw a leaked draft of the fifth assessment report, and there I saw that they increased the discussion on the possible role of the sun, but it's still relatively minor. Whether it's going to stay like that in the final version or not, I have no idea. Whether they're going to augment it with more references, I don't know.
Let's just be clear. You said the models don't include the real effect of the sun, and the real effect of the sun is
6 or 7 times larger.
because
They only consider changes in the solar irradiance.
and the reason it's 6 or 7 times larger is
Well, you measure it to be this way. If you look at the changed cloud cover or at the
Right.
oceans.
Exactly.
in cosmic rays.
Sir?
I think it was about 8 months ago that the CERN experiment validated the correlation that Svensmark had proposed between the low-level clouds and the cosmic ray influx. And was it the case, I think 8 months ago, that the CERN...
I think it was 2000, they published it in August, but I think it was August a year and a half ago.
Oh, was it wrong? Okay, my memory is... I
Um,
don't know how people older than me hang on that. Anyways, this
time
proved-
flies when you're having fun.
This proved that that indeed these cosmic rays were creating clouds. Now, as far as I could tell, those results were enormous, but they were completely buried, and there has not been widespread coverage of that. You can let me know how that could be also, whether that
Okay,
somebody should do something and highlight that in a real big.
Okay, so the results of the that were derived in CERN, what they did in CERN, it's a group headed by Jasper Kirkby. They essentially repeated the experiment that Henrik Svensmark carried out in Copenhagen, but under more stable conditions. I mean, they have a better system which can be better controlled, or they can reach a more stable configuration. And they have shown that if you increase the atmospheric ionization, or the amount of ions in the chamber, you increase the formation of condensation nuclei. These are small particles the size of several nanometers. You then have to grow them to large cloud condensation nuclei, because in order to condense and form a water droplet, you need to have a cloud condensation nucleus, which is about 100 nanometers. So it's much larger. And the reason it's discarded in the, say, mainstream community is because they say, okay, you only proved that you now form the small nuclei. We still don't know how those things grow to become 100 nanometers. So if we don't know, let's discard it.
The final question I'll reserve, and that is, you had a very interesting chart that showed the distribution that the climate models generate. And you said that they could equally explain heating or cooling if that is
Yes.
what had happened. I'm not sure that that's something that the general public necessarily understands. So if you would, go back to that chart and explain it again, just so we can all make sure that we understand what it is that these models are really telling us. That
Okay,
one.
first, I should emphasize that this chart was in the draft report of the the draft version of the fourth assessment report. So it's not mine. It's supposedly the IPCC. The thing is that, I mean, we've all seen these charts of error bars. What is the radiative forcing contribution of different components with the error bars? We've seen that thing. You can now add those contributions with the error bars to get a probability distribution function telling you what is the probability that we heated the planet by, say, 3 watts per square meter, or we cooled it by half a watt per square meter. And this probability distribution function looks very wide, and the reason it's wide is because there is an effect called the indirect aerosol effect, which nobody knows how to calculate properly, and that's the fact that particles that we humans pumped into the atmosphere serve as cloud condensation nuclei, so we change the property of clouds and we caused the Earth to cool, but nobody knows how to calculate it. So it's a large error bar which translates into a wide probability distribution function. So with the same uncertainty, you can in principle say, with a small probability, but it is still there. I mean, the probability to win the lottery is much smaller than that. There is still a probability that we might have contributed a negative radiative forcing on the planet, and that the planet should have cooled, but it decided to warm for some reason.
Yeah, that was in the draft.
It was in the draft of the...
2007 report.
Yes.
It didn't show up in the final?
No, it didn't, because it's embarrassing if you look at the implications of it.
I need to grab it and bring it back.
Dr. Shabir?
That's the nice thing about leaked reports, that you can find those
All sorts of things.
all sorts of things, exactly.
Thank you so much for coming down and speaking with us today. Thank you all for being here.